Hello. So I'm going to now lecture on Chapter 14, Blood Vessels and Blood Pressure. So to begin, we'll discuss cardiac output and blood pressure. So cardiac output is the volume of blood pumped each minute by each ventricle. And the cardiac output, which is expressed in mil per minute, is calculated by taking the stroke volume, which is the mils of blood pumped by each ventricle per contraction or beat. That's the stroke volume, times the heart rate, which is beats per minute. So we have mils of blood per beat and beats per minute. That gives us the cardiac output in mils of blood per minute. The average heart rate is 70 base pairs per minute. The average stroke volume is about 70 to 80 mils per beat. That's the volume gain coming out of each ventricle. The average cardiac output is 5,500 mils per minute. That is 5.5 liters per minute. And 5.5 liters is actually the total volume of blood circulating our blood vessels in our body. And so every minute, all the blood in our body is being circulated through our circulatory system. So it's pretty amazing when you think about what the heart is doing. And to trigger the contraction of the heart, we have the SA node, sinoatrial node, causing 90 action potentials per minute. And in terms of how the heart is regulated, we know that the sinoatrial node is triggering the depolarization, and that this is controlled by the cardiac center of the brain, and both sympathetic and parasympathetic nerves impact this process. So sympathetic nerves trigger the fight or flight response. So under the fight or flight response, which we have under a situation, for example, where we're having anxiety or an emergency, the neurotransmitter norepinephrine will help keep sodium channels open, which increases the heart rate. The parasympathetic nervous system helps to induce relaxation. So the parasympathetic nervous system will have the acetylcholine neurotransmitter trigger the opening of potassium channels, which will slow the heart rate. And now we can take a look at those effects of the sympathetic and parasympathetic nerves on the pacemaker potential from the sinoatrial node. So before we looked at this, right, you have the red showing the pacemaker potential, which is a depolarization caused by the opening of the sodium channels. Then this depolarization triggers the opening of the voltage-gated calcium channels, and then after the voltage-gated calcium channels are open, the potassium channels open, and they cause the repolarization. And this repolarization is needed to open these sodium channels that trigger the depolarization, right? So we have this very clear cycle. So sympathetic stimulation will lead to an increased frequency of action potential. So in the top, we saw there were 2 action potentials in this time period. There's going to be 3 when, for example, after the sympathetic nervous system influences the sinoatrial node. And then in contrast, if we have a relaxation signal for the parasympathetic nervous system, we can see there, instead of being 2 action potentials, there's going to be 1, right? So everything is a little bit slower. This stimulus is caused by the increased opening of the sodium channels to trigger more depolarization events. And then the parasympathetic nervous system is going to act on the potassium channels to be creating a more repolarized state. And that's why we're having, since it's more repolarized, it's slowing down the frequency of the action potentials. So the stroke volume is regulated by three variables. The first is the end diastolic volume. So I'm going to remind you that diastolic volume is diastolic means that it is happening during the relaxation period of the ventricles. So this is the end diastolic volume represents the volume of blood in the ventricles at the end of diastole. Sometimes people call it the preload, and the stroke volume, which is the volume of blood pumped per ventricular contraction or per beat of the heart, that increases with a bigger end diastolic volume. Another variable regulating the stroke volume is the peripheral resistance found in the arteries. So as the ventricle, the left ventricle is pumping blood into the aorta, there is going to be friction, right? Because there's this huge contraction of the ventricle pushing blood into the aorta. It has some elasticity, so it's going to expand a little bit, but it doesn't expand indefinitely, right? It has a resistance. There's going to be pushback by the aorta to have some resistance, so that not all the blood is going to leave the ventricle. Most of the blood will leave, but not all of it, being pushed into the aorta by the contraction of the left ventricle. So this peripheral resistance is inversely related to the stroke volume. So that means the more resistance there is in the aorta, that means the less volume of blood is going to be moved from the left ventricle into the aorta. And we call this peripheral resistance the afterload. So what I want to show you now on this diagram is the application of that equation I showed you on the first slide, which is the Frank-Starling, illustrates the Frank-Starling law of the heart. And if we look on the x-axis, we can see the ventricular end diastolic volume in mil. If we look in the y-axis in this graph, we see the stroke volume. So for a given end diastolic volume, if we have the sympathetic nerve stimulation, as shown by this pink arrow, what we see is that for a given end diastolic volume, let's say for here example, without this sympathetic nerve stimulation, we're going to have this lower stroke volume. However, if the sympathetic nervous system increases the number of action potentials, we're going to see the volume of blood that is moved out of the left ventricle into the aorta is going to increase for a given end diastolic volume. So check it out. This is the higher stroke volume, and if there's even more sympathetic nerve stimulation, it's going to be even higher. So what we can see is that having more action potentials are going to trigger a stronger contraction, and that stronger contraction is going to push out more blood out of the ventricles for the left ventricle into the aorta. For the right ventricle, it's going to pump the blood into the pulmonary artery. So another interesting thing about the heart is that the more stretching basically there is in the heart, the heart muscles, the bigger the contraction will be. So if we look from A going up to D, we can see that this is a unstretched heart. Remember, this is the actin and the myosin. The myosin shown in blue, the actin shown in black, and we know how that works for contraction of cardiac and skeletal muscle, right? So if you increase the distance to 2 micrometers by stretching it out, there's going to be more tension for contraction in the stretched muscle, the stretched sarcomere, than the unstretched sarcomere, right? And then if we stretch the sarcomere again into C, we see it's going to be even a stronger tension and a stronger power for contraction, right? So tension is related to the power of contraction. And then if we have D, the 2.4 micrometers, the biggest stretch in the sarcomere, then we're going to see it has the most tension and power for contraction. So what this graph is showing is that we have on the x-axis the length of the muscle, and then the y-axis we have relative tension. And the key point of this graph is showing this shift with the norepinephrine that stimulates the sympathetic stimulation of the heart. So let's take a look at the a muscle length that's 80% of its optimum, right? So we see that the relative tension is kind of low. It's maybe about 5%, right? But if this heart muscle is stimulated by the sympathetic nervous system, by norepinephrine, we'll see that the tension for the same length of muscle would be increased to about 30%. So the sympathetic nervous system effect on contraction is very significant. You get a much more powerful contraction with the stimulation by the sympathetic nervous system. So I'd like to now summarize what I just talked about. So we have over here cardiac output. This is determined by the cardiac rate being multiplied by the stroke volume. So sympathetic nerves both increase the cardiac rate and they also increase the contraction strength, which leads to an increased stroke volume, right? And I've shown you also how the stretch is important for the contraction length. And then the other important variable is the end diastolic volume. And the more end diastolic volume we have, the bigger potential we have for a bigger stroke volume. And this is all shown in the black dark arrow, solid arrows. We see this is the effect of the sympathetic nervous system to increase cardiac rate and to increase stroke volume. In contrast, the parasympathetic nervous system that favors relaxation versus the sympathetic that triggers the fight-flight response, the parasympathetic nerves actually reduce the cardiac rate, right, by reducing the frequency of the action potentials, and they also reduce the peripheral resistance. And as the resistance is lowered, it's actually lowering the blood pressure in the arteries.